Welcome back, everyone. This is Dr. Gallenstein, and we are here again for lecture number 11. Okay, so in the last lecture, we began to think about what are some techniques that we can use to solve the omitted variable bias problem and allow us to get a coefficient estimate that we can interpret causally. Okay, and I mentioned that the best method is if we could do a perfect experiment where we could randomly assign who receives some intervention and who doesn't. But we don't always have that luxury. Okay, and so again, we're continuing in this section of the class where we are learning how to identify causation. We don't always have the luxury of using the randomization method, which we talked about in last lecture. And so what we're going to do today, and continuing for several more lectures, is learn some techniques that we can use to identify causation, solve that omitted variable bias problem, even when we don't have randomization. Okay, and we'll find that some of these methods in some way kind of mimic the characteristics of randomization without actually having the randomization. Okay, so the first method that we're going to look at is called propensity score matching, and that's the topic of today's lecture. And with that introduction, let us begin. All right, so again, I'm just going to quickly review omitted variable bias, although of course you have previous lectures that you can go back for a more thorough discussion. Now remember that as economists, we want to get unbiased estimates of the relationship between variables, right? And in fact, we really want to understand, or oftentimes we really want to understand, the causal relationship between variables. We want to know what is the cause, or what is the causal effect that X has on Y. How does X cause a change in Y? All right, that's what we want to know. But one of the biggest barriers to that is omitted variable bias. Omitted variable bias is the bias that's caused when we exclude relevant variables from our regression, and those variables are also correlated with the independent variable that we are interested in. All right, so we want to try to solve that problem. All right, so again, just consider this generic multivariate regression model. We have our dependent variable y, independent variables x1, x2, and x3. And let's say that we really want to know the effect that x1 has on y. That means we want to know what is the causal impact that x has on y. If I introduced more x1, what effect would that cause? What change in y would that cause? All right, that's what I want to know. And that would be beta 1. So I want to know I want to get an unbiased estimate of beta 1. All right, that's what we want to do. Okay, but the omitted variable bias problem is that if we have a variable that is missing from the data set, or at least missing from the regression, so z here. So if there exists some z, and this z omitted from the regression, all right, if there exists some variable z, and this variable z is correlated with x1, and it is correlated with y, then there will be omitted variable bias. All right, and our problem is that there's almost always a z. There's almost always something that we're missing. So we're almost always going to have omitted variable bias. How do we solve this? All right, now the solution number 1 that we talked about in the last lecture was if we randomly assigned that variable of interest. We randomly assigned x1. Some people got x1 and some people didn't. So we randomly determined who received x1 and who didn't. If we can do that, if we can randomly assign it, then that x1 variable, that variable that we're interested in, will be statistically independent. It's no longer correlated with other variables. It's no longer correlated with the variables that are missing from the model, and therefore there will not be omitted variable bias for that variable. All right, now that's the best way of solving it, but we oftentimes don't have that ability. We rarely do we have the ability to randomly give away some intervention, to randomly determine who has the variable of interest and who doesn't. Very rarely do we have that opportunity. So that means we need to talk about some techniques that we can use even when it's not randomly assigned. Okay, we need to talk about some techniques that we can use when it's not randomly assigned. All right, so this is going to be solution number 2. If we do not have a randomly assigned variable, and like I said, we are rarely able to conduct economic experiments, all right, then we need to use a different technique. We need to use different techniques, all right? In this lecture and in subsequent lectures, we will discuss methods that mimic randomization and can control for omitted variable bias, even when we do not randomly assign the variable of interest. We're going to call these techniques quasi-experiments, or quasi-experimental techniques. These are techniques that will try to mimic randomization. They will try to mimic the consequences of randomization so that we can get this unbiased treatment effect, this unbiased relationship between the variable of interest and the dependent variable. Okay, so we're going to use quasi-experiments. That is the second solution. Today we're going to do one example of quasi-experiments. All right, so let's do quasi-experiments. So quasi-experiments use econometric techniques to mimic random assignment. So quasi-experimental techniques that we will talk about in this course will be propensity score matching. There's one technique. I'll talk about this today. Another technique is a natural experiment. Another one is instrumental variables. I'm going to talk about these two in the next lecture. And then finally, we'll talk about difference and differences. All right, so these are 4 different techniques that we can use to mimic random assignment, even when we have not randomly assigned our intervention. All right, today we're going to talk about propensity score matching. It's one of these quasi-experiments, one of these quasi-experimental approaches. Okay, so now because today is the first lecture that we're talking about quasi-experiments, I want to do a little bit of an overview. I just want to talk about a couple of things that will give us a little bit of a background for as we go through these quasi-experiments. All right, just a handful of things. We're just going to review randomization one more time to make sure our intuition's clear. I'm going to talk about a concept called observables and unobservables. All right, that'll be particularly important today. And then lastly, I want to talk about the relationship between these methods, these quasi-experimental methods, and the assumptions that we need to make for these methods to be valid. All right, so I just want to talk about that structure. I'm going to do this background, and then we're going to jump right into propensity score matching, our first quasi-experimental technique. All right, so randomization versus quasi-experiments. All right, so randomization involves randomly assigning observations in the sample data to either a treatment or a control group. Quasi-experiments use other means to mimic randomization when randomization is not possible. All right, so that's the basic difference. Randomization is a real experiment. We really randomly assign who gets the intervention, who gets the treatment, who doesn't. Quasi-experiments try to mimic that when it doesn't exist. It tries to mimic that randomization when the randomization is not actually there. Here's an example. We want to know the relationship between individuals' test scores and their ownership of a textbook. Okay, this is the same example we used from last lecture. We want to know the causal impact of ownership of a textbook on students' test scores. So what is the causal impact of owning a textbook? If a student owns a textbook, how much does that increase their test scores? That's what we want to know. We want to identify that effect. Okay, so then here's a regression that has test scores as the dependent variable and textbook as the variable of interest, the variable that we're looking at investigating. And so we want to get an unbiased estimate of beta 1. Okay, so if we randomize, we randomly determine who receives the treatment, the intervention, and who does not. All right, so let's imagine that we have a sample of 500 students. We want to know the impact of textbooks on test scores. So we randomly select 250 students and give them textbooks. The other 250 students do not receive textbooks. So in this case, we have this textbook variable. It equals 1 if they receive a textbook, and it equals 0 if they don't. Okay, and in this case, this textbook variable has been randomly assigned. That means that the students for which text equals 1, that means the students that have received a textbook, the students that have a textbook, the students for which the variable equals 1 is randomly determined. It's randomly determined which students have a textbook and which students do not. And in that case, so that if that treatment assignment is random, then this should achieve statistical independence. What does that mean? That means that the treatment group and the control group are the same on average. When I say that, I mean the group of students that own a textbook is on average the same as the group of students that did not receive the textbook. All right, so those two groups of people, the 250 students that got it, 250 students that didn't, those two groups of people are the same on average. Now, another way of putting this is to say that the treatment variable, this text variable, this treatment variable is not correlated with other variables. All right, so statistical independence implies these two things. These two things are effectively the same. The treatment group is the same as the control group on average, or the treatment variable is not correlated with other variables. All right, so this means that the text variable is not correlated with other variables, and therefore there will be no bias in our estimate of beta 1. We will not have omitted variable bias. All right, so that's randomization. Quick review of it to make sure we reinforce the concepts. If the treatment is randomly assigned, we should achieve statistical independence, which means the treatment group will be the same as the control group on average, and the treatment variable will not be correlated with other variables, included or excluded from the model. All right. So now what we do with quasi-experiments is we want to mimic that. All right, we want to mimic that. So if the treatment assignment is not random, we will not have statistical independence. This means that the treatment group will not be the same as the control group on average. So let's say we didn't randomly assign the textbook, but instead we just went in and we just went into a population of students and we collected data and we just observed who has textbooks and who doesn't. In this case, the ownership of textbook is not random. Some students have the textbooks, some students don't, and there's some reason why some students have it and some people don't, and some students don't. All right, so in this case, the group of students that owns the textbook will not be the same as the group of students that don't own the textbook. They won't be the same on average. And this treatment variable, this text variable, will be correlated with other variables. You know, probably students that have more income are more likely to own a textbook, and so the textbook variable will be correlated with income. And probably students that are more highly motivated for their education will be more likely to own a textbook. And so the textbook variable will be correlated with students' commitment or motivation level for their education. Okay, so if it's not randomly assigned, then the treatment group will not be the same as the control group on average. And the treatment variable is going to be correlated with other variables, which means we might have variables that are excluded from the model, but that are correlated with the treatment variable, which means we can have omitted variable bias. And so what these quasi-experiments do is they attempt to mimic randomization. Today, what we're going to look at is we're going to look at how can we try to establish a treatment group and a control group that are the same on average, even when the treatment was not randomly assigned. All right, that's what we're going to try to do today. We're going to try to mimic randomization by creating a treatment group and a control group that are the same on average, even when the treatment variable, the textbook variable, was not randomly determined. All right, we're going to try to mimic randomization using our data. All right, that's what we're going to look at today with propensity score matching. All right, but just in general, what do quasi-experiments do? We try to mimic randomization by some other means. All right, and we're going to talk about several different ways of doing that over the next couple lectures, starting today. All right, so that's the first part of this background. The next part of the background is I just want to introduce a concept, and we'll use this later in the lecture. I want to introduce a concept called of distinguishing between variables that are observable and unobservable. Okay, so I'll use this term observables and unobservables. Okay, observables are variables or characteristics that we can measure and have data on. Okay, observables are variables or characteristics that we can measure and that we have data on. All right, so observable characteristics like age and income and gender and things that we can measure. Things that we can measure and we have in our data set. Those are observables. All right, an unobservable is a variable or a characteristic that we do not have data on and or cannot be measured or cannot be easily measured. Maybe it's very difficult to measure it. So unobservables are oftentimes things like ambition or ability or confidence or proactivity. These things are hard to measure. It's hard to measure how committed I am, how proactive I am, how confident I am, how ambitious I am. These things are hard to measure. And so it's hard to have data on these things. These things we would often call unobservables, unobservable characteristics. We can try to measure them, and so in some way they're observable, but it's difficult. It's difficult to get data on these variables, on these characteristics. Okay, so that's just distinguishing between observables and unobservables. All right, this will become more important later in this lecture. I'm gonna make it clear, why does it matter to distinguish between variables that are observable and unobservable. Okay, this will be important today. All right, and then the last thing I want to do as background is I want to just discuss how do these different methods work. So I mentioned a moment ago that we're using quasi-experimental methods, and we've got several different possible methods. We have propensity score matching, we have natural experiments, we have instrumental variables, we have difference and difference. There's other methods, but these are the 4 that I'm going to talk about in this course. And every time we use one of these methods, we have to make certain assumptions. All right, so I want to talk about the structure of using these methods. When you go to use one of these methods, you need to be aware of the assumptions that underlie the method. Each one of the methods is based on a set of assumptions. So each method is based on assumptions. If those assumptions are true, if those assumptions hold, then when you use the method, you will be able to observe causation. You will be able to successfully mimic randomization. Okay, so if the assumptions hold, then you will be able to mimic randomization. All right, so then what we need to do every time we talk about these methods and use these methods, we need to be clear about what the assumptions are, and we need to discuss whether or not we think that those assumptions will hold. Before we run the regression, before we implement one of these methods, we need to address whether or not the assumptions hold. All right, so what we're going to do for each of these different methods is first I'm going to talk about the assumptions, then I'll talk about how the method works, and then when we use it in practice, we're going to do that at the end of the lecture. When we use the method in practice, the very first thing that we will do is see if we can validate the assumptions. Can we provide any evidence that the assumptions for this method are true, that they hold? If we can validate the assumptions, then we can go ahead and use the model. We can use the approach. If we can't validate the assumptions, then we cannot necessarily conclude that the method, that one of these quasi-experimental methods, will allow us to get the causal impact, will allow us to get an unbiased estimate of the effect of the variable of interest. Okay, so I just want to make that clear. When we use these methods, step number 1 is to think about the assumptions and to see if you can validate the assumptions, to think about whether or not these assumptions are true. All right, that is step number 1. Before you use the method, think about the assumptions. All right. So with that background, let's begin propensity score matching. This is quasi-experimental method number 1, propensity score matching. All right, first, as I introduce this method, I'm going to take some time here to talk about the intuition, to understand what is this method, why would we use it, and what is this method trying to accomplish. Okay? So the first step here, I'm going to go through the intuition. Then I'm going to talk about validating the assumption, or talk about what the assumptions are, and then we'll look at it in practice. All right, but first, intuition. So the intuition here is that what we're going to do when we use propensity score matching is that we want to match treatment individuals, all right, people that receive the intervention in question, all right, with control individuals, people that did not receive the intervention. Okay, so thinking back to our textbook example, what we would do here is to imagine a scenario when the ownership of a textbook is not randomly assigned. All right, so imagine a scenario in which the ownership of a textbook is not randomly assigned. Okay, so that means my treatment group, the group of people that own textbooks, and my control group, the group of people that do not own textbooks, are not going to be the same on average. All right, we're not going to have that statistical independence. Okay, so in that case, what we're going to do instead is we're going to match people from the treatment group to the control group. We're going to find people in the treatment group that have very similar characteristics to the people in the control group. We're going to match them. We're going to pair them up. We're going to match treatment people to similar or comparable control people. And then we're going to look for the treatment effect by comparing similar people from the treatment group to similar people from the control group. Okay, so now we're going to be matching people. Why do we do this? The basic idea is if we match similar people, we might be able to construct a treatment group and a control group that are the same on average because we're selecting people. We're picking out people that are the same. We're taking the people in the treatment group and then we're selecting people from the control group that are similar to those people from the treatment group. Okay, and so basically what we're doing is we are creating similar populations. We're trying to construct. We're trying to use our data to create treatment and control groups that are the same on average, even though we didn't randomly assign the interventions to the textbooks. All right, so okay, so let's keep going and try to make this more clear. Now, remember. So let's break this down. Let's say we have a sample of 500 students, all right? And what we've done here is we don't have an experiment. We did not randomly assign students to receive textbooks and not to receive textbooks. Okay, this is not a randomized experiment. Instead, we go to a population of students and we just collect data. We collect data on a population of 500 students. And when we collect data, we find that some students own textbooks and other students do not own textbooks. All right, so some students own textbooks, so text equals 1, and other students do not own textbooks, so text equals 0. So there are some students in the sample that own a textbook. For these students, the textbook variable equals 1. This we can say is our treatment group. All right, it's not a treatment group because it was randomly assigned. It's just the group of people that own the textbook. It's the group of people that own the variable of interest, the textbook variable. And we can say that this is our control group. Again, this was not randomly determined in this example, but instead the control group is just the group of students that so happen to not have textbooks. All right, so textbook equals 0. Okay, so this is a basic framework. Now, typically, we would go in, collect data on our 500 students, and we would just run a regression on the whole sample of data. All right, so we would just run our regression. We have our test scores here, and then we have our textbook variable here, and our different independent variables. All right, so and the textbook variable equals 1 for students that have a textbook, and textbook variable equals 0 for students that do not have a textbook. What this regression does is it effectively compares the average for the sample of students with the textbook to the average of the sample of students without a textbook. We're basically comparing the treatment group to the control group. when we run this regression. So that's what we're effectively doing. We're comparing the group with the treatment, so the treatment group, with the textbook, to the group without the treatment, all right? So the students that do not have a textbook. We're effectively just comparing this group of students to this group of students. Well, the problem is that we already know that since textbook was not randomly assigned, that the sample of students with the textbook will be different than those that do not have the textbook. This group of students will be different from this group of students. There could be all kinds of reasons why this group of students is different from this group. These students probably come from wealthier families. These students probably have maybe they probably have older siblings that purchased the textbook in the past and so are able to inherit the textbook from their older siblings. So maybe these students come from larger families. Maybe these students live closer to the school. Maybe these students are going to be different from these students in all kinds of ways. Okay, so this group of students is going to be different from this group of students. We don't have statistical independence. All right, so that's our problem. This implies that the text variable will be correlated with other variables that are included and excluded from the model. And so we're going to have omitted variable bias if we just run this standard regression. Well, with propensity score matching, we do something a little bit different. So instead, what we do is we match students that have textbooks to similar students without textbooks. We will then compare the matched groups of students. And by matching treatment and control students, we will be able to say that our treatment group and control group are the same on average. All right, so we're trying to mimic the effects of randomization. Now remember, if the textbook variable was randomly assigned, then we would be able to say that these students are the same as these students. But we can't say that in this case because it was not randomly assigned. Well, with propensity score matching, we're trying to mimic the randomization by matching treatment students to control students. And so here, we're going to take our sample of students that have the textbook and our sample of students that don't have the textbook, and we're going to try to separate them into groups and match them according to their characteristics. And so in this case, let's say let's just use one example. We're going to match students based on the income of their family. Okay, and so here are the population of students with textbooks. Here's the population of students without textbooks. And what we're going to do is we can separate these students into high income, medium income, and low income. And then these students into the same income brackets. So some of these students will be in the high income bracket, some of them will be in the medium income bracket, some of them will be in the low income bracket. And then instead of comparing the entire sample of these students to the entire sample of these students, instead we're just going to compare the students that are comparable. We're going to compare the treatment students that have high income to the control students that have high income. We'll compare the treatment students that have medium income to the control students that have medium income, and so on. So we match students. We match students that have similar characteristics. These two groups of students have similar characteristics. They both are in this high income category. These students have similar characteristics. They're both in the medium income category. These students have similar characteristics. They're both in the low income category. And so we basically we match treatment students to control students based on their observable characteristics. And when we do that, we hope that we will be able to create basically a control group that is the same as the treatment group on average, because we're distinguishing between their different characteristics. Okay, so then let me keep going. Now, the way that we do this, now in this example, what I've done is I've basically just given an illustration based on matching students for one variable. So in this case, what I've done is I've matched students based on the income variable. I've matched students. I've said these treatment students are the same as these control students with respect to the income variable. Okay, so I've matched them based on one variable. Well, matching them based on one variable is not going to be enough. We want to match them on as many variables as possible. How do we do that? Well, what we do is we create something called a propensity score. And then we match people based on their propensity score. So instead of in this example, I've just picked one variable, income, and I've matched students based on their income. I've matched students based on this one variable, income. Well, one variable's not enough. We got to do lots of variables. So what we do is we create something called a propensity score. And then we match people based on their propensity score. Rather than any one or two variables, we match them based on their propensity score. All right, the propensity score is the probability that someone will be in the treatment group as a function of numerous variables in the data set. All right. And so what we're going to do is by comparing individuals between the treatment and control group that have similar propensity scores, we can identify the causal impact of the treatment so long as certain assumptions hold. All right, so what we're going to do is we're going to take our entire sample of students and we're going to generate a propensity score. The probability that they would actually end up in the treatment group. All right, that's the propensity score, the p-score. So propensity score, I'm going to call it the p-score. Not to be confused with p-values in hypothesis testing. All right, this is the p-score. The p-score is the probability of being in the treatment group. And so what we're going to do is we're going to generate p-scores for the entire sample. For all the sample for all the treatment and control students, all the sample, we're going to calculate p-scores. And then we will match students in the treatment group to students in the control group based on their propensity score, based on their p-score. And the idea is that if the students have similar p-scores, if they have really similar p-scores, then the students are comparable. They're the same on average, which means that if they have similar p-scores, then we have mimicked randomization. We have created a mimicked randomization by matching students based on their p-scores. If students have similar p-scores, then they should be comparable on average, and we can compare them. We can create these matched pairs. Okay, so that's what we're going to do in propensity score matching. That's the intuition. All right, let me summarize it. All right, so here's the intuition. If the treatment is not randomly assigned, then the treatment group will not be the same as the control group on average. And that implies that there will be omitted variable bias. So we try to solve that. So the way we try to solve that is we match people from the treatment group to people in the control group. By matching, we can get a treatment group that is the same as the control group. To do this matching, we use the propensity score. We generate a propensity score, and we match people based on the propensity score. All right, so that's the intuition, is we're creating these matched pairs. And we're saying that if we've matched students from the treatment group to the control group based on their p-score, then basically if two different people have very, very similar p-scores or the same p-scores, then they must be the same. They must be very, very similar people, and so therefore we can compare them and use that comparison to determine our unbiased effect. All right, so that's the intuition. Now let's go into the details. All right, now, like I said when I was doing the background, I said that every time we use one of these techniques, we have to make certain assumptions. And these assumptions are critical. They're very important. Okay, we have to make these assumptions. If these assumptions hold, then we are able to conclude that we don't have omitted variable bias, and we've solved the omitted variable bias problem, and we have an unbiased effect. Okay. If the assumptions do not hold, then we will still have bias. Okay, so it is critical to understand what the assumptions are before you use a method. I can't stress this enough. Before you use one of these methods, you need to know what the assumptions are. And then you need to be able to make an argument for whether or not those assumptions hold. If they do not hold, if these assumptions do not hold, then we will have omitted variable bias. All right, so we need to know the assumptions, and we need to validate the assumptions before we can use these methods. All right, so now what are the assumptions that we would use for propensity score matching? What are the assumptions that we have to make for using propensity score matching? All right, so assumption number one. Assumption number one is called selection on observables. So I mentioned before that. This distinction between observables and unobservables. Okay, and so the first assumption is called selection on observables. So let me explain what this means. All right. So selection on observables means that whoever receives the treatment was determined entirely by observable characteristics. All right, so here's the idea. Selection, when I say selection, that means who is in the treatment group, who has the treatment and who does not. All right, so the question is, what are the characteristics that determine whether or not someone is in this treatment group versus the control group? What are the characteristics that determine whether or not the students own a textbook or do not own a textbook? What are the things that determine that? Now, if you remember a moment ago, I said that there's going to be lots of things that are different between the treatment group and the control group. There's going to be a lot of reasons why some students own textbooks and some don't. One reason why some students own textbooks is because maybe wealthier students are the ones that can afford to buy the textbook. Okay, so that's one reason. So that's one factor, one characteristic that determines whether or not someone owns a textbook or not. That is an observable characteristic. I can observe how much income these students or their families have. So if the ownership of a textbook is determined entirely by these observable characteristics, if it's determined entirely by how much income the family has, the size of the family, the age of the student, etc., if it's determined by all these observable characteristics, things that I can observe, then we have, quote, selection on observables. However, if ownership of a textbook is determined by other things, things that we do not observe, things like, say, the level of motivation that the student has. The level of motivation is going to be very difficult to observe that. It's very unlikely that we have a variable in our data set that accurately measures how motivated the student is. And so if that motivation determines whether or not the student owns a textbook, then we have selection on unobservables. Okay, so now one of the assumptions that we have to make for the propensity score matching is that we have selection on observables. That means observable characteristics. Observable characteristics determine whether or not someone is in the treatment group or in the control group. Whether or not someone is in the treatment group or the control group is determined entirely by observable characteristics, not by unobservable characteristics. All right, this is a tough assumption to make. Let me keep going here to make sure this is clear. So when I say selection on observables, what I'm speaking about, when I say selection, what I'm speaking about is why some students have the textbook and other students don't. So we've said, okay, in this example, the textbook is not randomly assigned. We're just going into a population of students and collecting data. And when we do that, we're going to find that some students have the textbook and other students don't. And so now when we look at that, we say, well, why do some students own the textbook and other students don't? This is the selection process. There's some reason. There is some reason or some reasons why these students own the textbook and these students don't. There's some reason why these students are the ones that have the textbook and these students don't. The question is why? What are the variables? What are the factors that determine whether or not a student owns a textbook? What are the factors that determine whether or not a student owns a textbook? Are those factors observable or are they unobservable? Okay, so selection on observables means that the reason why the treatment students have textbooks, right, the reason why a student is here, and the control students do not, all right, the reason why the control students do not have textbooks is due entirely to observable characteristics. That means that the variables in our data set contain all the information that we need to explain why the treatment students have the textbooks and the control students do not have the textbooks. That's selection on observables. That means that we have the data that explains why some students have the textbooks and other students don't. That's selection on observables. If we have variables in our data set that will explain why students have the textbooks and why some students have it and some students don't, then we can say we have selection on observables. If, however, we think that there are factors that we do not observe that affect whether or not a student has the textbook or does not, if we think there are some variables that we do not observe that impact whether or not the student has the textbook, then we have selection on unobservables, in which case the assumption of the propensity score matching approach does not hold. All right, so let me go back to this example that I used about income. Let me use this example to illustrate what I mean. Okay, so selection on. Okay, so let's say we've gone in, we've collected data on 500 students, and we've found that 200 of those students have textbooks and 300 students don't. All right, so let's say we've done that. 200 students have textbooks, 300 students don't. The question is, why do these students have the textbook and these students don't? Okay, selection on observables would mean that we can explain why these students have it and these students don't, based entirely on data that we have observed. So let's say that the students that have the textbooks are from wealthy families. The only reason why these students have the textbooks and these students don't is because these students come from wealthy families and these students come from lower income families. If that's true, if the only thing that is affecting why these students have it and these students don't, if the only thing that determines that is income, then we have selection on observables. Because we can observe how much income they have. We can observe how much income the family of these students have. And therefore we have selection on observables. The factors that determine who's in this group and who's in this group, those factors are observable. We have data on them. So if we can say that all the factors that determine whether or not a student is here versus here are observable characteristics that we have in our data set, then we have selection on observables. However, all right, now let me give an example of when selection on observables would be violated. All right, so here's an example. So let's say that whether or not a student has the textbook is also influenced by how committed that student is to their education. Students that have a higher level of commitment are more likely to own a textbook than students that have a low level of commitment. Let's say that that's true. If that's true, we probably do not have a variable in our data set that measures the student's level of motivation, which means the student's level of motivation is unobserved. It's an unobservable. However, this unobservable characteristic determines, it affects whether or not a student is in the treatment group or in the control group. That means we have selection on unobservables. And if we have selection on unobservables, then propensity score matching does not work. We will have bias. So if we have selection on unobservables, then we will have bias. Okay, so you need to be very careful before you use propensity score matching to be sure or to make an argument for why you think that this assumption, this selection on observables, is going to hold. Why will this assumption be true? Can we say that that whether or not a student is in the treatment group is entirely based on observable characteristics, characteristics that we're able to observe? All right, so that's assumption number 1, selection on observables. Assumption number 2 is called common support. Common support. Okay, so the common support assumption is that there are people in the treatment group and people in the control group that are comparable. Now remember, what we're doing here is that we are going to match people in the treatment group to people in the control group based on their propensity score. We're going to match them based on their propensity score. All right, now if we're going to match them, then we need to know, there needs to be people in the treatment group and the control group that are comparable. That means if we take the individuals in our treatment group, we need to be able to find individuals in the control group that have very similar observable characteristics to the people in our treatment group. Or we could say again, we need to be able to find, so we're going to generate propensity scores for everyone in the data set, and we need to find people that have very similar propensity scores between the treatment group and the control group. If we don't have that, if our control group is very, very different from our treatment group, and there's no one that has a similar propensity score, then we're not going to be able to use the method. We're not going to be able to create matches. We're not going to be able to find people in our control group that are comparable to the individuals in our treatment group. In which case, the common support assumption will not hold. Okay, so those are the two assumptions. All right, let me reinforce this. So the common support assumption means that there are comparable individuals in the treatment and control groups. Now remember, because the textbook variable is not randomly assigned, on average, the treatment students will be very different from the control students. But if the common support assumption is true, then there will be some control students that are comparable to the treatment students. Basically, we will be able to find students in our treatment group that have very similar p-values to students in our control group, or vice versa. We will be able to find students in our control group that have very similar p-scores to the students in our treatment group. We will be able to create matched pairs or matched groups between these two groups of students that will be very similar on average. So we'll be able to mimic randomization by creating matched groups or matched pairs. Okay, those are our two assumptions. Now I just want to make clear what the propensity score is. I'll make this even more clear in a moment. The propensity score is a single number that indicates the propensity or probability of receiving the treatment. All right, so this is a stylistic way of saying it. The propensity score is the probability that one of the individuals in your data set will be in the treatment group. So that means textbook equals 1, or whatever the treatment variable is equals 1, conditional or given the observable characteristics. All right, so it's the probability of being in the treatment group conditional on all these observable characteristics. All right. Now, if the assumptions hold, if the assumptions of the propensity score matching approach hold, then we will be able to get an unbiased estimate of the impact of textbooks on test scores. We'll have no omitted variable bias. It'll be the causal impact of textbooks on test scores. It'll be the ATT, the average treatment effect, the causal impact of textbooks on test scores, if our assumptions hold. All right. Now, with all of that said, let's discuss what does this look like in practice. I'll review that quickly here in the lecture, and then we will get to Stata. All right, so now, in practice, what is the propensity score? How do we validate the propensity score? How do we validate the assumptions? What does it look like to run a regression? And then what are the different matching procedures? All right, we're just going to do a quick overview of this, and then we're going to jump into Stata and show what it looks like in practice. All right, so what is the propensity score? All right, so like I said, the propensity score is the probability of being in the treatment, or probability of receiving the treatment, or probability of having the treatment. All right, so the probability of owning a textbook given the observable characteristics X. The probability of being in the treatment group conditional on the observable characteristics X. All right, so how do we calculate the propensity score? What we do is we regress the treatment variable on the observable characteristics. So we run a regression of the treatment variable on the observable characteristics X, and then we generate a predicted value, a predicted treatment value. And this predicted treatment value will be the probability. It'll be the probability of being in the treatment conditional on the observable characteristics X, so these variables in your data set. Now, one thing that you should recognize here is that this t variable, the treatment variable, is binary. Right? It's a binary variable. It takes 1 or 0. 1 if you're in the treatment group, 0 if you're not. 1 if you have textbooks, 0 if you don't have textbooks. Okay. So when you have a binary dependent variable, you need to think, well, what are the models that I could use? If I have a binary dependent variable, then I need to use a binary dependent variable model. All right. Well, that gives us that brings us down to the linear probability model or the low jitter probit model. We usually use probit, so linear probability or probit model. Now, in this case, what we're doing is we're generating predicted probabilities. We're generating the predicted value of t hat, which the predicted value of t hat is equivalent to the probability. So we are generating predicted probabilities. That should remind you what model we should use. All right. So what is the p-score? The p-score is the predicted probabilities of a probit model of the treatment variable regressed on independent variables from the data. So we use a probit model. So we're going back to our example of textbooks. All right. Textbooks is the textbook variable, the treatment variable, is a binary variable. It equals 1 if you own a textbook, 0 if you don't. And so we've regressed this using a probit model using a bunch of the independent variables from our data set. And the p-score is the predicted probability generated from the probit model. And so this should ring a bell. Here we see a reason why we need to use the probit model. We need the predicted probabilities for the p-score. The p-score are the predicted probabilities. So we could not use a linear probability model here to generate the p-score because predicted probabilities from the linear probability model would be irrational. They could be less than 0 or greater than 1. So we need to use a probit model. All right, so we use a probit model to generate the predicted probabilities, the predicted probabilities of being in the treatment group. And these predicted probabilities are the p-score. The p-score is the predicted probability. All right, so that's what we do. We could generate the propensity score. Now, we need to think about the assumptions. Remember, can't stress this enough. You know the assumptions, think about the assumptions. Are the assumptions true? Assumption number 1 is selection on observables. Assumption number 2 is common support. Let me just clarify. Common support. Okay, so assumption number 1, selection on observables. Assumption number 2, common support. We need to be able to validate or make arguments for why these assumptions are legitimate. So how do we do that for assumption number 1? Assumption number 1 is selection on observables. Okay, how do we do that? We cannot validate this assumption empirically. Now, I might dabble in speculating using the data in a minute when we get into Stata, but strictly speaking, we cannot validate this assumption empirically. We have to think. We have to make an argument. We have to make an argument for whether or not this assumption will hold. All right, if we use the textbook example, we can think, well, do we think that we will have selection on observables in the textbook example. Now, certainly we can imagine that students that have higher income will be more likely to own textbooks. In that case, that certainly there is selection on one observable. That's selection based on income. The problem is that we can also imagine that students that have a higher level of motivation are also more likely to own a textbook. That is an unobservable characteristic. Motivation is an unobservable characteristic. And so if I can think of an unobservable characteristic that will determine whether or not someone has the treatment, then I cannot assume selection on observables. There will also be selection on unobservables. All right. So if I'm using my textbook example, I will not be able to validate this assumption. Assumption 1 is hard to validate. Assumption 1 is, it's hard to make an argument that assumption 1 is going to be true. Because we can almost always think of some unobservable characteristic that will affect whether or not we have the treatment, whether or not an individual has the treatment. But we do the best job that we can. Now, maybe we can argue that motivation will affect whether or not the student has a textbook, but maybe we can argue that that's going to be very minor. It's not going to be very important. That's going to have a very small impact on whether students have the textbook. It's mostly due to income and other observable characteristics. Well, then we might move forward with assumption 1. We might move forward with it if we can say that selection is based almost entirely on observables. Okay, but assumption 1 is hard. It's hard because it's hard to justify that there's selection only on observables. All right, but you need to give an argument for it. So if you're trying to use propensity score matching, you need to give an argument. You need to argue for why you think that selection will be based entirely on observable characteristics. That you can use observable characteristics to entirely explain why the people that have the treatment are the ones that have the treatment. All right, that can be difficult. But you have to use your intuition to make an argument. We'll talk about that when we get into Stata. All right, assumption number 2, common support. The common support assumption, we can use our data. We can use our data to see whether or not we can validate this assumption. All right, so we can use our data to validate this one. All right, we can use our data to do that. How do we do that? Well, first what we do is we calculate our propensity score for everyone in the data set, and then we create a plot. We plot out the propensity score for the treatment group and the control group separately, and we see whether or not those propensity scores overlap. Let me show you what I mean by that. All right, so I'm taking 2 examples from the handbook of impact assessment. I highly recommend reading the propensity score matching section in the handbook of impact assessment that you can find online. This will be very, very helpful. The handbook of impact assessment was put out by the World Bank. It's a very helpful resource. You can find it on their website, or you find it with the materials attached to the course. Okay, so what you would do is you would plot out the density. You plot out the density of the propensity scores. All right, propensity score goes from 0 to 1. You plot out the density of the propensity score for the treatment group and the control group. So in this case, this line here, this is the density of scores for participants or the treatment group. And here's the density of scores for the non-participants or the control group. And you see whether or not these densities overlap with each other. You can see from this example that the density for the propensity score for the treatment group, this curve here, overlaps considerably with the density of the propensity score for the control group. So this is represented here, region of common support. So there's considerable overlap between the treatment and control groups. This is a good sign. This would be an example of strong evidence for common support. That means you're going to have people that are in your treatment group. That's the curve on the right. You're going to have people in your treatment group that have very similar or the same propensity scores as people in your control group. All right. So basically, there are some people in your treatment group that have a propensity score of, let's say, 0.3 here. And you also have people in your control group that have a propensity score of 0.3. Now, there's a lot more people in your control group that have a propensity score of 0.3 than there are in your treatment group, but that's okay. You can match these people, the people that have a propensity score of 0.3 in the treatment group, to people that have a propensity score of 0.3 in the control group. All right, so this is a good example of strong common support. This, if you saw this, you would have strong evidence that the common support assumption holds. Here it is an example of weak common support. So here again, on the right is the distribution of propensity scores for participants, those that are in the treatment group. And on the left, you have the distribution of propensity scores for the control group. And now you can see that these two distributions do not overlap very much. There's only a very small region of the data for which these two populations overlap. All right, so this is the region of common support. This is the region where they overlap with each other. In this case, there's not going to be very many people in the treatment group for which you can find comparable individuals in the control group. This would be weak evidence of common support. If you saw this, you would be very concerned that propensity score matching is not going to be a good approach. All right, now here I'm plotting this out using data from Stata. This would be an example of very strong common support. So this red line is a density, an empirical density for the control group, and the blue line is an empirical density for the treatment group. The empirical distribution of propensity scores for the treatment group and an empirical distribution for the control group. So empirical distributions of the propensity score are using the kernel density function. You can look at lecture number 1, lecture number 2 to get a review of this. Okay, so this would be an example of very strong common support. The treatment group and the control group are very similar. They overlap with each other a lot. The highest density of propensity scores is right around 0.6. And that's the same for the control group and the treatment group. So there's a lot of overlap here. There's very strong evidence for common support. All right, I'm going to do some more examples when we do Stata. All right, so that's our discussion of validating the assumptions. We'll do a little bit more of that when we get into Stata. All right, the last thing I want to talk about is when we use propensity score matching. Like I said, what we're going to do is we're going to match people in the treatment group to people in the control group. And there's different ways of doing that matching, and I'll show you the Stata command for the different ways of matching. So I'll just kind of highlight them here. There's one called nearest neighbor. So in that case, what we do is we take each treatment individual and we match them to the most similar control individuals according to the p-score. So for each treatment individual, we find the control individuals that are most similar based on their p-scores. All right, radius matching. This is where each treatment individual, it's matched to control individuals within a particular range of p-scores. And then kernel matching. This is where each treatment individual is matched to all control individuals with greater weight given to those with more similar p-scores. All right, so here are just some different options for ways that we can perform the matching. The kernel matching is probably the preferred approach. This is probably going to give you the most robust results, so we will emphasize the kernel matching approach when we do Stata. All right, and then lastly, the problems with propensity score matching. The biggest problem with propensity score matching is that first assumption, selection on observables. The selection on observables is a very hard assumption to make. And if there is selection on unobservables also, then our results will be biased. So if you think that there is selection on unobservables, that means we need to use a different method. All right. So problems with propensity score matching, there we go. Those are the drawbacks of propensity score matching. Now let's do it in Stata. All right, here we go. In this exercise, I'm going to use the data set wages underscore PSM, PSM standing for propensity score matching. In this data set, this should look very familiar. I'm using this wages data set. We're analyzing wages. And just like the last lecture, I'm going to look at the impact of a training program on wages. All right, so let's go ahead and get started. You see here that I've started my do file with a couple of lines of code in it. I've done that because I just want to make sure that I remember how these codes work. Okay, all right, so let's get started. Lecture 13, propensity score matching. All right, so in this demo, we want to know the impact, I should say the causal impact of a training program on people's wages. Okay. But the training program was not randomly assigned. Instead, the training program was offered at some charge. Let's see, it's offered for free at a local community center. So this is just some free program, a free training program offered to people at a local community center. Anyone who wanted to attend could attend. All right. So the training variable is not randomly assigned. All right, what implication does this have? Okay. This means that if we ran a simple regression model, we would have omitted variable bias. Okay. So this means, so because it wasn't random, this means the treatment group, aka people that receive the training equals 1. All right. The treatment group is going to be different from the control group. So where the training equals 0. All right. So this means if we run simple regression, we get omitted variable bias. So let's just run it. Let's run simple regression wage on training. All right. So if we did that, if we ran this simple regression, we would get a coefficient estimate, of course. Our coefficient estimate is going to be 1.77. Okay. And it's statistically significant at the 1% level. All right. But, all right, so we get an estimate of 1.77, significant at 1%. But we know that this will be biased. All right, so that means we need to solve it. We need to solve the bias. How? In this lecture, we will use propensity score matching. All right. First, we need to install the code that Stata uses to perform propensity score matching, or from here on out, PSM. All right, so this is a code to install a particular code. All right, this is a code that will allow you to install a command called psmatch2, and psmatch2 allows you to perform propensity score matching. Okay, so you're just going to install that step 1. That's just a little issue when we use Stata. We need to install the package that would allow us to perform this using a Stata command. All right, so now I'm going to do two examples. Example 1 and example 2. All right, so example 1, I just have two different training variables that will allow me to illustrate two different things. So example 1, I'm going to use the training variable, and then in example 2, I'm going to use training 2. These are just two different variables. I'm just going to use them to illustrate. All right, so example number 1. All right, as I made very clear, step number 1, when we use propensity score matching, step number 1 is know, and validate the assumptions. All right, very important. All right, so assumption 1. What's assumption 1? Selection on observables. All right, what's assumption 2? Assumption 2 is common support. All right, how do we validate assumption number 1? We can't really validate this empirically. That means we can't really use our data to validate this. Now I'll do one thing in just a minute to try to get an idea of it, but really we need to think about it. We need to look at our data set. We need to say, what are the factors that determine whether or not someone received the training? What are the factors that determine whether or not someone received the training? Are those factors all observable / in our data? Those are the questions we need to ask ourselves. So if we think about it, what are the factors that are going to determine whether or not someone receives the training? Well, the education level of the person might affect it. How many number of years of experience they have at their job might affect it. You know, if you have more experience, then maybe you don't need the training, so you're less likely to go to the training. Ethnicity, I don't know. Gender, that's not obvious. Whether or not someone's married, that might have a lot of effect on it. Married people might have a lot less time to go to a training. So that might affect it. But can we think of anything else? Anything that isn't included in this data set that might affect whether or not someone goes to a training? So let's see. We definitely have selection on observables. So we definitely have observables. All right. So education, experience, married. These are all pretty clear. Those probably affect it. But are there any unobservables? Okay. Now the unobservables are not in the data set, right? Because they're unobserved. Are there any unobservables that would affect it? What do you think? Unobservables. Maybe this motivation. This motivation is probably going to affect it a lot. People who are really motivated to perform well in their career are probably much more likely to attend the training. Maybe people that have weak professional skills. So they really need the training. So people that really need the training, go. Basically, we can think of a lot. We can think of a lot of unobservables. So this would imply that the assumption 1 does not hold. And so here, this illustrates it. It's hard to have an example where the assumption number 1 holds. It's hard to think, it's hard to say that there is no selection based on unobservables, that the selection is only unobservables. That's a hard assumption to make. But now in practice, oftentimes propensity score matching is the best approach that we have It's the only thing that we have. It's the only tool in our toolbox. And so we might say, well, I'm not sure if there's selection on observables. I think there's also selection on unobservables. But even if we can't assume it, we might still move forward. We might still say, I think that selection is primarily based on the observable characteristics. I think that this is based primarily on observable characteristics. In fact, I can argue that people with more education are more motivated. So, even though I don't have a variable that measures motivation, I am indirectly controlling for that when I control for education. So I can try to make some argument. Okay, so I try to make some argument for why we can assume selection only on observables. Let's try to make some argument. All right, so I've just made some argument. So then I'm going to move on. Assumption number 2, common support. Actually, you know what? So there's really no good empirical way of validating this assumption. But one thing you can do is you can just look to see how well fit your probit model is. So let's do training. Let's do education, experience. I'm just gonna throw everything in, female and married. Let's just see how well this model fits the data. This is a very informal way. All right. How well does the probit model fit the data? All right. Very informal way of validating the very informal way of validating the selection on observables assumption. All right, we can look to see how well does the probit model fit the data. All right, obviously it's a probit model of training on the independent variables. So the pseudo R squared here, the pseudo R squared is 0.68. That's a pretty decent R squared. So maybe it's okay that we make assumption 1. Maybe it's okay if we make assumption 1. We will acknowledge it. We will acknowledge that assumption 1 may not hold when we discuss our results. All right, so basically we just want to make sure that we talk about assumption 1 when we discuss our results. Okay. Basically, when we discuss our results, we want to make sure that we just explain that maybe assumption 1 doesn't hold. All right, now common support. How do we validate this one? Well, the first thing that we need to do is we need to generate the propensity score. So generate the propensity score. All right, how do we generate the propensity score? Well, actually, we already started. The propensity score is the predicted probability of participating in the training, predicted probability of participating in the training from a probit model. Okay, so now we need to run a probit model where the training variable, the treatment variable. All right, so probit model with the treatment variable, in this case training, is the dependent variable. All right. And then we include independent variables that we think will impact participation in the training. All right, so let's think about this. Probit model, training. What are the variables that we thought would affect it? We said education, we thought experience, and we thought married. So let's do that. And then what we're going to do is predict, and we'll type p-score. So this is the predicted value from the Probit model. So we're going to run this and get our predicted probability. So now we have our p-score. Let's look at it in the data. Let's open up our data. Here's our p-score. This p-score is a number between 0 and 1. Remember, it's a predicted probability from the Probit model, so it's bounded between 0 and 1. And what this does is it gives me the probability that an individual received the training. All right, so we can go through and we can just look. Here this person 1 was in the training. They went to the training, and they have a p-score of 0.99. There's a 99% chance that this person is in the training, went to the training. Person 2 was not in the training. The p-score, the probability of person 2 being in the training is 0.22, 22%. Okay, so very low probability of person 2 being in the training. All right, person 1 was in the training. They have a propensity score of 0.99, so 99% probability of being in the training. All right, so et cetera. It goes down. Every individual in the data set has a propensity score, some predicted probability that they would participate in the training. And so what we're going to do is we're going to match people based on this propensity score. We're going to try to find people that received the training that have, that have propensity scores and match them to people in the control group who have similar propensity scores. That's the idea behind propensity score matching. But first, we need to validate the common support. The common support is the idea that there are going to be people that overlap. There are going to be people in the treatment group and people in the control group that have very similar propensity scores. And therefore, that we will be able to control. We will be able to match people between the treatment group and the control group. Okay, so then how are we going to do that? So we've generated our p-score, and now what we want to do is we want to create a plot. We want to plot out the empirical distribution of the propensity score for the treatment group and the control group. All right, so we're going to use a command called two-way. That means this is going to be a plot. This is going to be a graph that has two different plots on it. We're going to use the k-density. So this is the empirical distribution of the p-score if training equals 1. All right, and we're going to give this a color. It's going to be color blue. All right. And then we're also going to plot the k-density. All right, the empirical distribution of the p-score if the training equals 0. All right, so this is the treatment group. It's going to be in blue. And then this is going to be the empirical distribution of the propensity score for the control group. All right, and we want to give this thing a legend. All right. All right, so the first group is going to be the treatment. The second group is going to be the control. All right, it's kind of a long code. Okay. And then we want to give that second one a color. We'll just specify that it has no color, so it'll be black, I think. All right, so now this is going to be our graph. We're going to plot it out. Let's see what it looks like. So it's running. What is it going to look like? Are they going to overlap or not? If they overlap a lot, then it validates our common support. If they don't overlap, it doesn't validate. All right, now, do they overlap? Now, sometimes it can be kind of tricky to make an argument for common support or not. But let's look at these distributions. We'll find that most of the control observations are way down at the bottom. So most of the people in the control group have propensity scores near 0 or near 0.1, very low. For the treatment group, we'll find that most of the observations in the treatment group are way up here near 1. So they have propensity scores at like 0.9 or 0.99 or 0.95, way up here. We'll find, we can see here that the control group doesn't have any. There's no one in the control group that has a propensity score that is above 0.9, even though the vast majority of the treatment group have values above 0.9. So when I look at this, I can say they overlap for quite a bit of a range. That means that there are values for the treatment group that are all the way down near 0. But I would look at this and I would say that there's actually quite a bit of a problem here. The vast majority of the treatment group is way up here near 1, and there is nobody in the control group to compare these people to. There's nobody in the control group that has a similar propensity score to the vast majority of the treatment group. So you say the vast majority of the people in the treatment group have a propensity score near 0.99 or 0.95. And there is nobody in the control group. There's nobody in the control group that has the same propensity score. So when I look at this, I'd say this does not look good. This does not look good. This does not show strong common support, because the vast majority of the treatment group has no one in the control group that is comparable. There's no one in the control group that's comparable. All right, so if I did this, so if let's say I'm doing this research and I'm looking to validate, I want to use propensity score matching, and these are the results. I'm a little bit skeptical about assumption 1, although I can make an argument. But then when I go to try to validate assumption 2, I find this. I find that the vast majority of the treatment group does not overlap with the control. At this point, I would be very concerned about proceeding with the PSM approach. I don't think that the evidence for my assumptions is very strong. So I will probably look for other methods instead of the PSM method, and only use PSM if the other methods do not work. All right, I'll explain that later. Basically, I can't validate the assumptions of the other models, then I might use PSM. So at this point, I'm just going to stop. I'm not going to finish. I'm not going to do the regression here because I don't think that this is going to give us unbiased results. We have very poor common support, and it's difficult to validate assumption 1. All right, so for this training variable, I'm scrapping it. I'm not even doing it because I don't think I have strong evidence for my assumptions. All right, so then let's go on to example 2. Example 2, I just have another variable, and I'm calling it training 2. This is a different variable for training, but the same idea. All right, I'm just using it for illustration purposes. All right, now, for this one, again, step number 1 is always validate assumptions. All right, so we've got to validate the assumption. Now, assumption 1, this is the same as from example 1. So we'll skip this. The exact same discussion. So we're going to skip this in example 2 because this training variable is, again, it's just another variable that equals 1 if they receive the training. But now the people that receive the training are different. Okay, we're just imagine that that the training variable is training 2 instead of training 1. All right. Okay. So now let's assumption 2, common support. All right. So now let's try to validate this. All right. So again, we're going to do the same thing. Probe it. Training 2, education, experience, married. All right. Predict p-score 2. All right, so let's run that. All right, so here is our here's our p-score. We've generated our p-score. All right, so now I'm going to come in here. I'm going to produce the same plot, but now it's for p-score 2. All right, so training 2, training 2. All right, so let's plot this out and see what the common support looks like. Okay, now we're talking. This has very strong common support. So you can see that the vast majority of the control group has propensity scores between maybe 0.15 and 0.4. And then the vast majority of the treatment group has propensity scores around 0.4. Okay, so there's very strong common support. These things overlap over almost the entire range, and there's a lot of the population that overlap with each other. So the large amount of the population overlap here. So this is very good, very, very, very good common support. All right, very good evidence of common support. All right, so we will proceed with propensity score matching. We'll proceed with propensity score matching. We can make an argument for assumption 1, and we have great evidence for assumption 2. All right, so now let's run the regression. Let's do the propensity score matching regression. All right, PS match 2. What do we do here? Here we type in all of our independent variables, so training, or all the independent variables we want to include. All right, education, experience, female, let's say, married. All right, and then we're going to put in our outcome variables. So that's going to be wage. All right, and then after comma outcome variable wage. And then out here, we're going to put the type of matching mechanism. I'm going to do kernel, because I think that's the best one. So then let's run it. And here we go. We have our propensity score matching results. All right. So what this is this gives us the propensity score matching results. So this code, what it does is it generates the propensity score. These results up here is the probit model that generates the propensity score. All right, and then it shows the treatment effects for the impact of the training on the outcome variable wage. And so in this case, the coefficient estimate for the impact of training on wage is, we find it right here, 8.13. You'll see that it's labeled the ATT, the average treatment effect on the treated. All right, so how would we interpret this? Interpretation. Participation in the training increases, participation in the training causes wages to increase by $8.23 per hour. Okay? And then we might add a caveat. This estimate was generated using propensity score matching. We believe that both assumptions hold. However, we acknowledge that perhaps assumption 1 does not hold, and if so, this estimate will be biased. All right, so we might just add a caveat that's basically explaining the fact that we use the propensity score matching, and there could still be some bias if especially assumption 1 does not actually hold. Okay, so there we go. That is our result for propensity score matching. I hope that you enjoyed the lecture, and I hope you have a great day.